3-minute preview of my paper, Comprehensive Assessment of Tropospheric Effects at a Wide Range of Frequencies Transmitted from LEO Satellites. The motivation for this project is that there's a growing interest in using LEO satellites for navigation, but there are limited studies on the tropospheric effects on these signals. So tropospheric effects include range delay, signal attenuation, and fading. And we use standard ITR methods, and we use theoretical modeling at all of these different frequency rates. And we consider 4 different regions that have very diverse climates. So the troposphere has dry gases and water vapor. Dry gases are stable, well modeled, but water vapor is highly variable and very difficult to model. So the range delay depends on the refractive index of the medium. So refractive index changes, the signal bends, and then it takes a longer path. The range delay has the contributions from dry and wet delay. Attenuation due to rain has different parameters, as shown here, depends on the rain rate and the path length and the specific attenuation. The attenuation due to clouds and fog also has a similar expression, and it depends on the cloud liquid water content. Attenuation due to gases also has a similar expression, but there are 2 parts to it. We have the dry air and water vapor attenuation. Scintillation fading. Tropospheric scintillation refers to the rapid fluctuations in the refractive index of the medium as the signal travels through the medium, and it reduces the strength of the signal, causing amplitude fading, and the amount of fading depends on the wet term of surface refractivity. The range delay results, Indonesia has the highest amount of delay, and the results at 5 degrees are much worse than at 30 degrees, but there's no frequency dependence. Attenuation due to rain, the results at 5 degrees are much worse than at 30 degrees. KU band, the higher frequencies have much worse attenuation, and Indonesia has the highest amount of attenuation. Similarly, attenuation due to clouds and fog, the results at 5 degrees are much worse than at 30 degrees and follow a similar frequency trend. And attenuation due to gases actually has it's very negligible for all of our frequencies of interest. And scintillation fading, again, follows a similar trend as the other attenuations, and 5 degrees have much worse results than 30 degrees. And we are validating the theoretical model with real data that's collected in Maui, Hawaii, actually on the summit of the Haleakala Mountain. We have our receivers and antennas. The authors would like to thank our sponsor, Air Force Research Lab. And yeah, if you want to know more about this, please look at the Navigation Journal, volume 72, issue 4, and this is my email ID if you have more questions. Thank you so much. That's all for today.